let's see. What I've shown you now is how to do a simple iterative process and a simple recursive process. I just want to summarize the design of simple machines for specific applications by showing you a little bit more complicated design, that of the thing that does doubly recursive Fibonacci, because it will indicate to us and we'll understand a bit about the conventions required for making stacks operate correctly. So let's see. I'm just going to write down, first of all, the program I'm going to translate. I need the Fibonacci procedure. It's very simple, which says if n is less than 2, the result is n. Otherwise, it's the sum of fib of n minus 1 and fib of n minus 2. That's the plan I have here, and we're just going to write down the controller for such a machine. We're going to assume that there are registers n, which holds the number we're taking Fibonacci of, val, which is where the answer is going to get put, and continue, which is the thing that's linked to the controller, like before. But I'm not going to draw another physical data path, because it's pretty much the same as the last one you've seen. And of course, one of the most amazing things about computation is that after a while, you build up a little more features and a few more features, and all of a sudden you've got everything you need. Okay, so it's sort of remarkable that it just gets there so fast. I don't need much more to make a universal computer. But in any case, let's look at the controller for the Fibonacci thing. First thing I want to do is start the thing up by assign to continue a place called done, called fib done here. So that means that somewhere over here I'm going to have a label, fib done, okay, which is the place where I go when I want the machine to stop. That's what that is. And I'm going to make up a loop. There's a place I'm going to go to in order to start up computing a fib. Whatever is in n at this point, Fibonacci will be computed of, and we will return to the place specified by continue. So so what you're going to see here at this place, what I want here is the contract that says, I'm going to write this with a comment syntax. The contract is n contains arg, the argument, continue is the recipient. And that's where it is. And that's where in other words, at this point, if I ever go to this place, I'm expecting that this to be true, the argument for computing the Fibonacci. Now, the next thing I want to do is to branch. And if n is less than 2, by the way, I'm using what looks like Lisp syntax. This is not Lisp. This does not run. What I'm writing here does not run as a simple Lisp program. This is a representation of another language. The reason I'm using the syntax of parentheses and so on is because I tend to use a Lisp system to write an interpreter for this, which allows me to simulate the machine I'm trying to build. Okay? I don't want you to confuse this to think that this is Lisp code. It's just I'm using a lot of the pieces of Lisp. I'm embedding a language in Lisp, using Lisp as pieces to make my process of making my simulator easy. Okay? So I'm inheriting from Lisp all of its properties. Fetch of n. 2, I want to go to a place called immediate answer. That's the base step. And that's somewhere over here, just above done. And we'll see it later. Now, in the general case, which is the part I'm going to write down now, let's just do it. Well, first of all, I'm going to have to call Fibonacci twice. In each case, I'm going to have to, well, in one case at least, I'm going to have to know what to do to come back and do the next one. I have to remember. Have I done the first fib or have I done the second one? Do I have to come back to the place where I do the second fib, or do I have to come back to the place where I do the add? In both cases, I'm going to need the value. In the first case, over the first Fibonacci, I'm going to need the value of n for computing for the second one. Okay, so I have to store some of these things up. So first thing I'm going to do is save continue. That's who needs the answer. And the reason I'm doing that is because I'm about to assign continue to the result, to the place which is the place I want to go to after, let's call it fib n minus 1. Big long name. Classic Lisp name. Because I'm going to compute the first fib of n minus 1, and then after that I want to come back and do something else. So that's the place I want to go to after I've done the first Fibonacci calculation. And I want to do a save of n, because I'm going to need it later, after that. Now I'm going to, at this point, get ready to do the Fibonacci of n minus 1. So assign to n the difference of the fetch of n and 1. Now I'm ready to go back to doing the fib loop. Have I satisfied my contract? And the answer is yes. N contains n minus 1, which is what I need. Okay. Continue contains a place I want to go to when I'm done with calculating fib of n minus 1. So I've satisfied the contract, and therefore I can write down here a tag after label after fib n minus 1. Now what am I going to do here? Here's a place where I now have to get ready to do fib of n minus 2. Okay? But in order to do fib of n minus 2, look, I don't know. I've clobbered my n over here, and presumably my n is counted down all the way to 1 or 0 or something at this point. So I don't know what the value of n in the n register is. I want the value of n that was on the stack that I saved over here so that I could restore it over here. I saved up the value of n, which is this value of n, at this point, so that I could restore it after computing fib of n minus 1, so I could count that down to n minus 2 and then compute fib of n minus 2. So let's restore that. Restore of n. Now, I'm about to do something which is superstitious, and we will remove it shortly. I am about to finish the sequence of doing the subroutine call, if you will. I'm going to say, well, I also saved up the continuation, since I'm going to restore it now. But actually, I don't have to, because I'm not going to need it. We'll fix that in a second. So we're going to do a restore of continue. Which is what I would in general need to do. And we're just going to see what you would call in the compiler world a peephole optimization, which says, whoops, you didn't have to do that. Okay, so the next thing I see here is that I have to get ready now to do Fibonacci of n minus 2. But I don't have to save n anymore. The reason why I don't have to save n anymore is because I don't need n after I've done fib of n minus 2, because the next thing I do is add. So I'm just going to set up my n that way. Assign n minus the difference of fetch n and 2. Now I have to finish the setup for calling Fibonacci on n minus 2. Well, I have to save up continue. And assign continue to the place which is after fib n2, that place over here somewhere. However, I got to be very careful. The old value, the value of fib of n minus 1, I'm going to need later. The value of Fibonacci of n minus 1, I'm going to need, and I can't clobber it, because I'm going to have to add it to the value of fib of n minus 2. That's in the value register, so I'm going to save it. Okay? So I have to save this right now. Save up val. And now I can go off to my subroutine. Go to fib loop. Now, before I go any further and continue and finish this program, I just want to look at this segment so far and see, oh yes, there's a sequence of instructions here, if you will, that I can do something about. Here I have a restore of continue, a save of continue, and then an assign of continue, with no other references of continue in between. The restore followed by the save leaves the stack unchanged. The only difference is that I set the continue register to a value, which is the value that was on the stack. Since I now clobber that value, and since it was never referenced, these instructions are unnecessary. Okay, so we will remove these. Okay? But I couldn't have seen that unless I'd written them down. Or is that really true? Well, I don't know. Okay, so now we've now gone off to compute Fibonacci of n minus 2. So after that, what are we going to do? Well, I suppose the first thing we have to do, we've got two things. We've got a thing in the value register which is now valuable. We also have a thing on the stack that can be restored into the value register. Okay, and what I have to be careful with now is I want to shuffle this right so I can do the multiply. Now, there are various conventions I might use, but I'm going to be very, very picky and say I'm only going to restore into a register I've saved from. Okay, if that's the case, I have to do a shuffle here. Okay, so because it's the same problem with how many hands I have. So I'm going to assign to n, because I'm not going to need n anymore. N is useless. The current value of val, which was the value of fib of n minus 2. Okay. And I'm going to restore the value register now. This restore matches this save. And if you're very careful and examine very carefully what goes on, okay, restores and saves are always matched. Okay? Now, there's an outstanding save, of course, that we have to get rid of soon. And so I restored the value register. Now I restore the continue one. Which matches this one. Dot, 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 dot. Down to here. Now I'm restoring that continuation. That continuation is the continuation of fib of n, which is the problem I was trying to solve, the major problem I'm trying to solve. So that's the guy I have to go back to who wants fib of n. I saved him all the way up here when I realized n was not less than 2, and so I had to do a complicated operation. Now I've got everything I need to do it, so I'm going to restore that. Assign to val the sum of fetch val and fetch of n and go to continue. So now I've returned from computing Fibonacci of n, then the general case. Now what's left is to fix up a few details. Like there's the base case of this induction, immediate answer, Yes, which is nothing more than assign to val fetch of n, because n was less than 2, and therefore the answer is n in our original program, and return. Continue. Bobble, bobble. Almost. And finally, fib done. Okay. So that's a fairly complicated program, and the reason I wanted you to see that, because I want you to see the particular flavors of stack discipline that I was obeying. Which, first of all, I don't want to save anything that I'm not going to need later. I'm being very careful, and it's very important. And there are all sorts of other disciplines people make with frames and things like that of some sort, where you save all sorts of junk you're not going to need later and restore it because in some sense it's easier to do that. That's going to lead to various disasters, okay, which we'll see a little later. It's crucial to save exactly what you're going to need later. It's an important idea. And the responsibility of that is whoever saves something is the guy who restores it because he needs it. And in such a discipline, you can see what things are unnecessary. Operations that are unimportant. Now, one other thing I want to tell you about, it's very simple, is that, of course, the picture you're seeing is not the whole picture. Supposing I had systems that had things like other operations, car, coulter, const, building a vector and referencing the nth element of it, or things like that. Well, we could get this level of detail, whatever it is, we can conceptualize those as primitive operations in the data path. In other words, we could say that some machine that, for example, has the append machine, which has to do const of the car of x with the append of the coulter of x and y. Oh, gee, that's exactly the same as the factorial structure. Well, it's got about the same structure. And what do we have? We have some sort of things in it which maybe registers x and y, and then x has to sometimes move to y sometimes, or x has to get the value of y. And then we may have to be able to do something which is a const. I don't remember if I need to like this in this system, but const is sort of like subtract or add or something. It combines two things, producing a thing which is the const, which we may then think goes into there. Okay, and there may be a thing called the car, which will produce, I can get the car of something, and maybe I can get the coulter of something, and so on. Well, we shouldn't be too afraid of saying things this way, because the worst that could happen is if we open up const, what we're going to find is some machine. Okay? And const may in fact overlap with car and coulter, and it always does, in the same way that plus minus overlap and are really the same business. Const, car, and coulter are going to overlap, and what we're going to find is a little controller, a little data path, okay, which may have some registers in it, some stuff like that, and maybe inside it, and they may also be an infinite part, a part that's semi-infinite or something, which is a lot of very uniform stuff, which we'll call memory. Okay, and I wouldn't be so horrified if that were the way it works. In fact, it does, and we'll talk about that later. So are there any questions? Gee, what an unquestioning audience. Suppose I told you a horrible pile of lies. Okay. Well, thank you. Let's take our break.